And welcome viewers, friends, foes, and neutrals to the Daily Space Weather Show. Coming at you with another 24-hour series of videos for you here at the Smash News Network, least busted name in news. Got some interesting activity going on in the weather, in space, also on Earth. We'll cover it. That's 171 angstroms SDO. We're going to speed things up a little bit today because we've got an Ask a Particle Physicist segment as well, not to mention a proton event caused by a long duration or associated with a long duration solar flare and plasma filament reorientation event happening earlier this morning in that southwestern limb where all the action's happening, your lower right. Here we're back to 304 angstroms wavelength, and let's move into these filaments suspended by the magnetic field associated with sunspot 3599. It still could produce large flares despite being long since out of view behind the southwestern solar limb. Lots of plasma raining back down toward the solar surface there. Here's 171 angstroms. And there was a massive coronal mass ejection emitted as well. We'll cover it and let you know if it's earthly directed or not a little bit later in the video. And before we cover anything like that, let's take a brief look at what's going on with the magnetogram. Also, there's 171 plus colorized magnetogram. One of the great composites you can get from the SDO Browse Data feature. Highly recommend you try that if you haven't. That is just today, March 15th, 2024. And let's see what's going on with volcanic activity. Abico has been exploding. There's some ash being emitted from the Paramushir Island volcano. Fernandina also in the Galapagos. Lava continues to advance toward the sea. Sulfur dioxide emissions reached 576 tons. Popocatépetl exploding. Fuego in Guatemala, Nevado de Ruiz, Revenador, and Sabancaya all erupting. Next, 90 days of earthquakes. And the 7 magnitude earthquake drought continues. This is the past 24 hours of 5 and greater magnitude quakes. Starting with an El Salvadoran quake at a 5.0 magnitude early this morning at 3:13 Universal Time. Then a couple of quakes in Japan, a 5.6 magnitude and then a 5.2 magnitude aftershock. And that's it. It's been pretty calm for the past 24 hours when it comes to earthquakes. Next, looking at some more space weather stats here with the 10.7 centimeter radial flux, now at 129 solar flux units, I think it is. It's pretty stagnant here, and we've got a pretty quiet sun in terms of sunspots, and radial flux, but quite a lot of filamentary activity going on, as we forecasted yesterday on the Daily Space Weather video. So there's the 1 year graph, and 128, 129, something like that. It's the black line is the radial flux, the red line is the sunspot number, the blue line is the Potsdam AP index, and here is our space weather enthusiast dashboard. No space weather storms forecasted by NOAA, but some geomagnetic unrest forecasted basically for right now. So we'll see what's going on with that first Earth magnetic moment from space for the past 4 hours. It's our space weather modeling framework model of our geospace magnetosphere movie. So that's what's going on in space for the past 4 hours in terms of magnetohydrodynamic pressure. Things are quite calm. We've got weak solar wind at the moment. Earth magnetic moment from the ground looking like this. It's also the last 4 hours, our ground magnetic perturbations map. And again, to reiterate, things are geomagnetically calm. Speaking of magnetism, geomagnetism that is, the KP index is at 1, KP1. Pretty uneventful when it comes to space weather, at least in terms of the solar wind stuff. ACE is only showing about 1.4 protons per cubic, only about 1 proton per cubic centimeter for the solar wind density. Solar wind velocity here about 415 kilometers per second. We did see a little bit of coronal mass ejection activity happening right in here. It was pretty weak, but there was some activity there on ACE. Discover's next. It's got a little bit of missing data there. The current activity is about 4.5 protons per cubic centimeter for the density. Solar wind velocity here a little under 440 kilometers per second. GOES magnetometers are next. And things are pretty smooth there at the GOES 16 and GOES 18. And next our magnetic sector. So Earth is persistently here in a North Pole magnetic sector. No crossover yet. It has extended, so we could spend even a couple more days in the North Pole sector. Keep in mind the magnetic environment can change with basically no warning. Here's our line of sight field plot depicting photospheric magnetism in grayscale, B field magnetism in blue, and the potential field surface source lines of red and green represent the north and south polar fields, which brings us to coronal holes. Coronal holes, we've got North Pole oriented ones here mainly, some South Pole making their way around in the east and northeast. Let's take a look at coronal holes from the perspective of the ever popular SDO. So no real well-defined coronal holes here. A bit of one in the northern hemisphere there. That's of North Pole orientation, I believe, right? That is, yes, North Pole orientation. And let's move to sunspots. Sunspots, sunspots. Wherefore art thou sunspots? Well, because of magnetism in the photosphere. Down to about 51 sunspots now, folks. So if you're spooked of an inactive sun, now's your time to get into the bunker. Tell all the people who are afraid of an active bunker, an active sunspot, tell your bunker people who are afraid of an active sun, it's time for them to get out of the bunker and for you to get in the bunker, because now we have a fairly inactive sun, only 50 sunspots. That's pretty weak activity indeed. So here's our flare probability monitor and scoreboard, and the likelihood of a large flare is not that high, but the likelihood of a coronal mass ejection is nearly 100%. So moving forward, we still have a massive number of massive filaments on the Earth side of the solar disk. We'll get to it a little bit later. And before we get to things like the proton spike that's happening right now, let's move on to sunspots. So there are sunspots from SDO. Let me get out of the way. And yeah, that's what about 50 sunspots look like. Pretty weak activity. Don't expect that to continue. Solar maximum is only about 7 months away. So that's what's going on. And let's cut back to energetic particles. So we did have an SEP, a solar energetic particle event. It was associated with a very long duration C-class flare. Follow us on Twitter if you want to see that. Somebody took a video of it called Keith Strong, Dr. Keith Strong, that is, and we shared his tweet. So if you'd like to see that in its close-up, slow-motion glory, x.com/smashomash is where you can find that. And if you don't want to follow us, that's on you. So here's this long-duration flare I'm talking about, and look how long this thing lasted. It started out at about 0 dark 45, and it didn't really end until about 12 hours. That's about a 12-hour duration solar flare there, folks. So that's a pretty lengthy solar flare indeed. It was only of a C-type class, about a C6, but a very long duration. And of course, you can see this proton event started showing up about 5 hours after it started, 5.5 hours or so. And of course, on the channel, we talk regularly about how we don't really think that solar flares cause coronal mass ejections. So, I don't say that. I say associated with coronal mass ejections, because here at the Smash News Network, we are into facts. That's how you become the least busted name in news. You just stick with the facts and let the chips fall where they may. Now, on that note, we're going to be covering something that we don't normally cover. It's our Ask a Particle Physicist segment. So every Friday, we typically have an Ask a Particle Physicist segment. So this week's, once again, is brought to you by the magician from Minsk. It's Eugene the Philosopher, so make sure you subscribe to his channel. Don't be a sociopath. Subscribe to Eugene's channel. It's our in-house particle physicist. So, once again, the magician from Minsk is going to take it away. Here comes this week's Ask a Particle Physicist segment. Take it away, Mr. Bagashov.
Okay, so since many people regularly suggest that solar flares cause coronal mass ejections, could you briefly explain why the opposite is actually more plausible? Alright, let's just keep reading. That is, why do some of us believe the coronal plasma filament movement causes the X-ray emissions known as solar flares, not the flare causing the filament to eject? Well, let's address the first one firstly, alright? So, I'm not sure, why do many people suggest that flares cause CMEs? I mean, I can see the argument, but the thing is, there are flares without CMEs, and there are CMEs without flares, so at least any significant ones. I guess it also kind of depends, it's a nomenclature issue. What do you call a flare? Because, there's an A and B and C class, which is barely noticeable, but is this a flare or is this not? Because if you count A or B, I'm not sure if there's AA class actually, but if you count B class as flares, the sun is constantly flaring. It's pretty much like a continuous flare happening on the sun all the time, right? But if we're talking about more strong events, at least C8 or something, or M1 even, then still we have CMEs without flares, we have flares without CMEs. So my kind of conservative position is that these are just different phenomena. So one can occur without the other. They can coincide if there's some really energetic, motion happening on the sun, etc. And speaking of why do some of us believe that the coronal plasma filament movement causes the X-ray emissions, known as the solar flares, not the flare causing the filament to eject? I don't know. We gotta ask some of you, because I don't suggest this, for example, so this is not a question for me specifically. Yes, when the filament is ejecting, there is a flare called Hyder flare, but it's not the usual, in air quotes, solar flare in the way it looks, even on the X-ray plot, it's very long, very how do you call it, smooth, it can last for many hours, whereas the regular flare, it happens roughly maybe 1 hour or something like that. Actually depends again what you count as the duration of the flare in the first place. So yeah, or maybe even whatever, you get the idea, hopefully. So yeah, there is a Hyder flare associated with the filament, but they are very rare compared to the flares in the active regions. So I don't know what exactly is implied here. This is not my position, and whatever. I guess one can ask a question, well then what causes the flare? But that's a whole separate discussion. My understanding, and it's far from being complete because I haven't studied this in a lot of detail. I have studied it to some detail, to enough detail to understand that it would take years of research for me to, kind of grasp it. So we have the sun, right, this orange circle, and we have coronal loops. So we have one sunspot, let's say here, one sunspot here, and one sunspot here, and we have a coronal loop connecting them where there's a pretty strong electric current is running, and this is kind of below the surface of the sun. We usually don't see it, but this thing is there anyways, but we don't see it, all right? But the magnetic field lines have to be closed. That's why I've drawn it like this as a circle. Let's just draw it with a bit more, wonkiness. There's something below the surface of the sun, probably, supposedly, right? This is what we see above it, and there's a big current, as I've said, and I think what happens is, for some reason, this current gets disrupted at some point, all right? so it terminates at some point. But since this essentially magnetic coil has tremendous magnetic energy associated with it, but the current is disrupted, so this magnetic energy has to go somewhere. The current is no longer there, so it cannot stay in magnetic form, if you wish. So it gets released. It gets released mostly somewhere here at the point of the disruption, right? The whole energy of the circuit gets released there. This is what Alfvén initially thought, and I think it's a pretty interesting model to consider. Now, why exactly can the current be disrupted? Well, I have two ideas. For example, we can have, again, when most of the flares happen, at least according to, your everyday astronomer, is when you have multiple sunspots of different polarities intermixed, right? So what that allows to happen, I think, is that you have kind of many oppositely directed current loops nearby. So one of them can disrupt the other, and that kind of breaks the current. So if the current is counter-directed in them, right, the green one flows in one direction, the red in the other, and they meet, don't how do you call it, don't cross the streams, right? So the disruption happens, and the flare happens, so all this magnetic energy is released. So that's one possibility. And then you have the double layer forming, where previously you've had current, and it accelerates the charged particles, and it also releases the energy in the form of photons, which we see and recognize as the flare, and all kinds of stuff like this is happening. Another idea I've had rests on the Weber's electrodynamics. So it's impossible in Maxwell's electrodynamics, but it is possible experimentally, all right? So I think it may hold water. So sometimes, if the current is very strong, I would claim you don't even need any opposite sunspot, kind of oppositely directed current. So just because the current itself is very strong, the magnetic repulsion from, let's say, this segment of the current and the next one, and they do repel in Weber's electrodynamics. They don't in Maxwell, but Maxwell is wrong because it has been demonstrated experimentally that this is the case. They do repel. So parts of this coronal loop may repel so much that the current would be disrupted once more, and this would produce the flare. So this would be kind of the second mechanism, but not really the mechanism, but like the second reason for the mechanism to happen. And the mechanism is as Alfvén described it, right? So you have the disruption of the current, which releases the energy of the whole circuit at the place of the disruption, mostly, but not only. And obviously it can also release a CME, it can energize the plasma around it and send it flying outwards. So this is my idea of how flares in general work. But I repeat, a lot of research is needed, but I think this makes sense, at least on some level. But then again, CMEs may happen even without it, but how do they happen without it? Well, that's a good question. Again, maybe something else is present, maybe it's not, I don't know. So this I'm not sure about this. And the opposite is more plausible, that CMEs cause flares. This is definitely not more plausible, because there's many more, I would claim, flares without CMEs than there are CMEs without flares. That would be my point. Okay.
Alrighty then. By the way, I have no idea what he said, as usual, because I do not watch the videos until after the premiere. So I actually see the Particle Physicist segment with you, and then the next day on Saturday I release it. Once again, make sure you subscribe to Eugene the Philosopher if you haven't. Thanks to Eugene for doing the Ask a Particle Physicist segment. So check out Eugene's videos if you haven't. Don't be a sociopath. Go subscribe. Next, we'll move on to star charts. So that's what's going on overhead right now, Lehigh Valley, Pennsylvania. We still got the sun up there, and let's move forward with a solar system forecast. There you go. That's where things will be in a week. We'll have a gibbous we'll have a gibbous waxing moon, a gibbous waxing.
Next, our astronomy photo of the day, and this one is some edge-on galaxy called NGC something or other. Remember, folks, Einstein said, never memorize something you can look up. Recognizing the finite properties of the human mind, it's NGC 1055. That's the astronomy photo of the day. Feel free to pause the video on this frame if you'd like to clip it for your desktop. And remember, YouTube viewers who use a mobile device, you can zoom in 8 times. That's why we don't really mind having a smaller window here. It allows us to have more stuff on the screen. There are a lot of pixels. A lot of pixels. Anyway, moving on to CMEs. And we better move these to full screen because this is bonkers. Bonkers, I tell you. Some pretty sweet CMEs. But are they earthly directed? That's the real thing people want to know, right? So we'll cover it. So there's LASCO C2 and C3. Quite good early this morning. Massive series of CMEs. So right there is on the C3. Here's the C2. We'll bring it back. Oh my God. So that's actually 2 events there at least. Maybe 3, but at least 2 events. So the one out of the west is a separate one than the one out of the south. The one out of the south is on the far side, though. So that's the unfortunate news. That's not only one CME, because if it were, it would be earthly directed. But it's not. It's 2 CMEs that are both behind the solar limb. So I looked for quite a while at this one, and pretty sure we ain't got no Earth-directed plasma at the moment. 421. So there's a much later view there. 7 o'clock on the C3. There's 421 on the C2. That's a pretty good view there. If you bring it back to 340, look at the density of the plasma in the center of that filament there. That's pretty sweet. And here comes some custom coronagraphs, and dag, not too bad. But first, stereo A and its difference imagery. And uh-oh, do we have missing data? Hold on, that's yesterday. Let's move this forward. There we go. Not bad, not bad. And you can kind of see the way it's 2 separate events there because there's missing data, so it moves ahead like a freeze frame. And the difference imagery is missing even more stuff, so let's just ignore that. But the raw coronagraph, you see that first event, and then there's 4 hours of missing data there, and you can actually see the second event there. It's almost like it started right there, or it stopped failing to send data. So, could have been associated with the proton event. There was a massive stream of protons on the way. It could have been behaving like a curtain, more or less. So let's take a look at our flary wavelengths. At least one of our flary wavelengths, 131 angstroms. Keep in mind, it's still part of the extreme ultraviolet spectrum. It's not really flares, as those are X-rays, a much higher frequency, higher energy photon. So there's 131. That fantastic long-duration C6 class solar flare, which caused a significant, but not all that fast, proton event. In other words, it took many hours for it to arrive. Of course, it may not be completely obvious when the protons were actually ejected. Things can be a little bit deceptive when there's a lot of stuff going on all at the same time. So anyway, let's get to filaments. Oh wait, we don't want to get to filaments yet. We got to show CMEs. Yeah, CMEs are kind of important, right? So hit it. Yeah, I guess CMEs are important. What do you think? So there you go. There's our synced imagery. And that is good stuff. So yeah, it's actually 2 events happening there.
maybe even 3, but certainly 2, and those plasma motions aren't on the Earth side of the disk. So, sorry, aurora chasers. That one's not going to be helpful for your auroras, I don't think. So, yeah, that's... you're not going to see a lot of motions on the Earth side here. It looks almost like one of these filaments kind of wraps around or something, but I don't think that's what's actually happening. I think it's some separate events. And really, even if that was just one event, it's still likely to miss to the southwest. So that's a great view there. We've got 193 angstroms difference imagery mixed in. And that's a pretty good mix. Equatorial zoom. And a close-up of the filaments associated with sunspot 3599. All right, let's blast through meteorology and our bonus segments since we are horrifyingly late already. First, one more series from that. You think that's good enough for the thumbnail, folks? Let us know in the comments what you think. We endeavor to read all viewer comments, even if we are unable to respond to them all. So yeah, and we get those videos from helioviewer.org, by the way, so we highly recommend that you try it out if you haven't. It's a little bit of work, but it's well worth it. So here come bonus features. Plasma filaments are first, and we've got a bunch of dense filaments on the Earth side still. Look at how many. Look at that. That's insane. Look at the center of the solar disk. I see 1, 2, 3, 4, 5, 6, like 6 or 7 of them right in the center of the solar disk, folks. That is a legit Earth-directed CME-ready star, if you ever did see one. Here is our... It's just colored imagery. It's essentially the same thing, except the gray imagery shows the prominences. It is the same wavelength, 65, 62.8 angstroms. But there it is. That's a lot of plasma filaments pointed right at Earth. So if you looked at that from the side, it would look all bumpy, like a bunch of plasma filaments that are in our current newly branded design for the SNN, the Smash News Network, the supposed name of news. So here are the past couple of hours, and there's still a lot of stuff going on down there in the southwest, and the likelihood of seeing an X-class flare down there remains. There is a shocking amount of material piled up, sort of behind and all around sunspot 3599, and solar flares happen kind of low in the corona. Like, they're not happening on the surface, folks. So there's still certainly ample ability for a solar flare, a large one, to occur in that southwestern limb. But that likelihood is diminishing as time goes on. Anyway, next are charging hazards. There you go. Surface charging hazards are non-existent. The GOES electron flux here is a little higher than NOAA forecasted. There's the one-year graph to contextualize the electron flux. It is a flowing of electrons measured at about 300 kilometers of altitude, the location of the F-flare. Here is the relativistic electron forecast model. These are the same electrons that we're talking about. They are... It's not to be confused with the total electron content. That is a different thing. This is just the electrons at the F-flare of the ionosphere. So, but there you go. It looks like NOAA will be off. NOAA will have forecasted low on the electron flux. Next, the layer where it's measured, the F-flare at 300 kilometers. If you go to 300 kilometers of altitude, does that constitute space? Yes. So that's what's going on in the F-flare. That is, quote, what's shaken, end quote. And it's literally what's shaken, or how fast it's shaken. Also, keep in mind, folks, the material up there is extremely diffuse, so it's not largely subject to the same forces that your sea level air are associated with. You know, the forces exerted on your sea level air are very different, namely gravity and massive air pressure, because it's in a soup. But up there, things are very diffuse because it's space. And the reason I say don't confuse it with the total electron content is because, well, the total electron content is all of the free electrons from ground level up to the inner portion of the outer Van Allen belt. So that's where your GPS satellites are located. They're at about 12.5. They're about halfway between the F layer of the ionosphere and the GOES satellites. So about 12,500 miles of altitude is where your GPS satellites are located. That's the free electrons between you and them, or your GPS handset and them. On the right is our maximum usable radio frequency. We close out space weather with the latest imagery from SDO. Has forecasting space weather become like a bodily function for you? Well, it has for me, so make sure you press the like button. Press like, and if you're new to the channel, don't forget to press subscribe. Otherwise, you might miss the world's most comprehensive daily space weather content. We even cover Earth weather, just for fun, because it's way too easy to forecast. So let's do it anyway. Check it out. There's a bunch of cold water in the North Atlantic. So if you're spooked of cold water in the North Atlantic, definitely bunker up. It's definitely bunker time if you're spooked of cold water in the North Atlantic. However, this is depicting sea surface temperature anomaly and ocean currents, and you'll notice that ocean currents are still making it to Ireland and Iceland. So the likelihood of Europe having a year without a summer it might be 0%. I think it's 0%, but let's just take a look. Look at the sea surface temperature anomalies. Ooh, look at how cold the Atlantic Ocean is. Oh, it's freezing there. Now, here's the Arctic Ocean. It's mostly frozen, so not a lot to see for sea surface temperature anomalies there. Here's the Indian Ocean. And oh noes, look how cold it is. The global coldists. Folks, who do you think are crazier? Do you think that the global warmists are crazier? Or the global coldists? Or that they're the same crazy? Or that, like, tell us what you think of global warming, global colding, global staying the same. We should start a cult. We should start a global climate stability cult where we're all convinced that the temperature is going to stay level. And, you know, we could be like level Earth, except we'll be level climate cultists. What do you think? That should be fun. That'll be fun. Any kind of a cult is fun. So fun. I don't know who would be the leader, by the way. Who would be the leader of the level climate cult? That's the level climate cult. That should be a thing. I'm gonna make a shirt that has a graph and it shows the climate rising and then just leveling off and just staying exactly the same. 72 degrees for 10,000 years. Dude, it's gonna be room temperature for 10,000 years, folks. Oh no. That's going to be terrible. What will I do? What will I do? All right. For all of you who come for the space weather and stay for the rants, you're welcome. To quote Nick Burns, your company's computer guy. You know, Jimmy Fallon, he fixes your computer, then he's going to make fun of you. That guy. You're welcome. Anyway, we showed satellite imagery. Here is the snow cover for the U.S., at least the lower 48. There's a snow cover for the planet, basically. Windy.com, it's fantastic. Weather.gov is a thing also. It's okay. It's not too bad. I mean, radar.gov is a little bit better. We'll show you that. There are your weather warnings, by the way. And check out the Gulf Coast. Some nasty weather. Some water spouts likely here off the coast of Well, Mississippi and Louisiana. So here comes some forecast. There's your pressure and precipitation forecast. And that's some harsh weather there making its way around the Gulf states. Like I said, be prepared for that, Gulf state people, because otherwise you could lose your fingertip. Oh, no. Oh, my fingertip. Oh, my God. I lost my fingertip. Dear God. So, moving along to, what else is going on here? Is my mic too short? What's happened? There we go. All right, perfect. And, that's your GFS 72-hour pressure and precipitation forecast. Cheers. Congratulations on surviving another work week so far, or another week so far, or another decade so far. It's been quite a decade, right? We're at the 4-year mark for do what now? This should be the year of do what now? Here's our positive snow depth change forecast in inches, 72-hour GFS model. Here's our total accumulated precipitation forecast, 72-hour GFS model. That's a lot of rain coming to Texas, Louisiana, Mississippi, and Alabama especially, but there it is. Cheers. Temperature anomaly forecast is the final forecast. The final forecast. The final forecast. Oh, it's in degrees Celsius. It's the same model. All right, enough of that. So it's there's lightning. That's another thing that occurs mainly in the Gulf states. Here is your current lightning map, courtesy of blitzachtung.org, and that's some pretty serious lightning here associated with there's probably a tornado there southwest of Houston. Dude, that is an intense thunderstorm. Don't be outside during that. That could be, let's just say, surviving a lightning strike is low in its chance for you. It's like a plane crash, only way worse. Anyway, congratulations on surviving another winter. Almost. It's only that long until a thing occurs where the sun crosses the Earth's equator, and the shadows become straight on the planet. It's called the equinox. And if you don't know what that is, you should have a high school level of physics to be able to understand our channel. But if you watch for a long time, you'll figure out what stuff you don't already know, and then you'll learn. Otherwise, you'll go, I thought I was supposed to be spooked. Spoked and spooked, like frightened on a bike. Spoked. I spoke of how I was spoked. I spoke about speaking, about spokes and being spooked. There you go. There's a poem for you. There's my latest. Please copyright that. ASAP Smash Staff. For God's sake. Copyright that. She says no. She's the worst. All right, anyway. No, she's done a bunch of things to optimize the website, so check out smashamash.com. Anyway, there's satellite imagery, there's water vapor imagery, and let's go back to the recap here. That's one of the things. And heavy storms. Dude. And Houston. Let's start calling it Houston. That'll anger somebody. Remember, folks, in the northern hemisphere, the most likely place to see a tornado is at the northwestern corner of the storm. So put that in your knowledge basin. Put that in your knowledge basin and let it condense into your condensed matter brain. Yeah, condensed matter. It matters, and you're made of it. That's the completion of the recap, and here's me jetting See you next time. In the meantime, may that solar wind be at your back.